Did you know that crawfish, an invasive crustacean species once responsible for more than $120 million in damages, has become the foundation of a food industry worth over $300 million annually in Louisiana, USA? From a destructive invader burrowing deep beneath the mud, crawfish are harvested, sorted, chilled, peeled, and packaged before making their way into the famous fiery red Cajun boils, beloved across America. So what allowed Louisiana to control, utilize, and transform this controversial species into a culinary icon of an entire region? Join Terran Works as we uncover the story right now. Crawfish are freshwater crustaceans closely related to lobsters and shrimp, but they do not live in the ocean. Instead, they thrive in shallow water environments, such as swamps, canals, bayous, and flooded rice fields. Because they often burrow and hide beneath the mud, locals gave them a simple, down-to-earth nickname: mud bugs, creatures of the mud. Their close connection to muddy wetlands and shallow waters is exactly what makes crawfish so unique. They are not only capable of surviving in the wild, but can also become part of human agricultural systems. In Louisiana, rice fields, wetlands, and the region's hot, humid climate create the perfect habitat for crawfish to flourish. Over time, these small crustaceans evolved beyond their role as simple field creatures, becoming a valuable food source, a source of income, and a powerful symbol of Cajun culture, appearing in restaurants, festivals, and outdoor crawfish boils across the region. But crawfish were not always considered a valuable resource. The problem began when they spread beyond their familiar wetlands and entered ecosystems that were not prepared to control them. In particular, the red swamp crawfish is an extremely adaptable species. It can survive in many types of freshwater environments, consume a wide variety of food sources, and reproduce rapidly under favorable conditions. In Europe, this species has already been recorded across 16 territories, impacting freshwater ecosystems through its fast life cycle, high population density, wide dispersal ability, and burrowing behavior. Ironically, the same traits that allow crawfish to thrive in Louisiana rice fields can also turn them into an ecological threat elsewhere. As their numbers grow beyond control, crawfish begin altering the environments around them. They burrow into pond banks, canal edges, and rice field levees, weakening the soil and increasing the risk of erosion and water system damage. Crawfish are opportunistic feeders, consuming everything from aquatic plants and small underwater organisms to fish eggs, while also competing with native species for food and shelter. Their constant digging activity can make the water increasingly murky, reducing the amount of sunlight that reaches the bottom. As aquatic vegetation declines, entire freshwater food chains can begin to destabilize. After the rice harvest season ends, many fields in Louisiana do not immediately return to the dry conditions of a typical farm field. Instead, farmers begin flooding the land, transforming areas that once grew rice into shallow wetlands filled with mud, leftover rice stalks, and microorganisms. The remaining rice stubble slowly decomposes, creating a nutrient-rich environment where algae, larvae, worms, and many small aquatic organisms begin to thrive. For crawfish, it is almost like a naturally prepared buffet. What makes this system especially unique is the crawfish's natural ability to burrow and hide beneath the mud. During dry or unfavorable conditions, they dig deep into the soil for shelter. Then, once the fields are flooded again and cooler water and natural food sources return, the crawfish emerge, begin feeding, growing, and continuing their life cycle. As a result, farmers are able to harvest not only rice above the surface, but also a living source of protein below it. This is why the rice crawfish farming model is often described as a form of two-layer agriculture. It does not require expanding farmland or separating itself from the existing ecosystem, but instead intelligently utilizes the mud, water, and leftover rice stubble already present in the fields. According to 2024 agricultural statistics, Louisiana has more than 367,761 acres dedicated to farmed crawfish production. This figure shows that crawfish are no longer just a minor byproduct of rice farming, but have evolved into a large-scale agricultural system. This is also what makes the model so remarkable from an ecological perspective. Louisiana did not simply turn crawfish into a commodity through uncontrolled harvesting from the wild. Instead, the state integrated them into a manageable agricultural cycle, creating a sustainable and continuous system. Once crawfish reach the right size, the quiet rice fields begin transforming into a massive outdoor harvesting operation. Across the flooded farmland, hundreds, sometimes thousands of traps are arranged in long rows. Each trap contains bait designed to lure crawfish inside. At sunrise, workers operate specialized boats that move steadily along the trap lines, repeating a sequence of actions that leaves almost no room for error. Lift the trap, dump out the crawfish, refill the bait, and place the trap back into the water. At first glance, the scene may appear calm and routine, but in reality it is an intense harvesting system where every movement is a race against time. Workers endure Louisiana's heat and humidity while their boats continue moving forward without stopping. On average, it takes only about 7 seconds to process a single trap. That speed directly determines the productivity of the entire workday. If the pace slows down, the harvesting rhythm breaks, trap schedules become misaligned, and the total crawfish yield begins to drop. Once removed from the water, crawfish cannot remain under the sun for long. They must quickly be collected into sacks, transported back to shore, and move through the next stages of sorting, washing, cooling, or shipping. Most importantly, they must remain alive. The moment crawfish die, the quality of the meat declines rapidly, causing their market value to fall. That is why every sack of crawfish arriving at shore represents a race between humans and time, where each small trap scattered across the flooded fields forms part of a food industry worth hundreds of millions of dollars. After leaving the muddy fields, crawfish enter their first major checkpoint: sorting. This is far more than simply separating large crawfish from small ones like with many ordinary agricultural products. For crawfish, sorting functions almost like a biological screening process taking place directly on the processing line. Each individual is evaluated based on size, health, survivability, and commercial value. Undersized crawfish may be separated and returned to the fields, allowing them to continue growing for another season. Large, healthy crawfish with strong movement and clean shells are placed into the highest value category, the group destined to be sold live to restaurants, seafood markets, or traditional crawfish boils. Meanwhile, weak, dead, damaged crawfish, along with mud, small fish, snails, or other unwanted organisms, must be removed from the supply chain immediately. For crawfish, being alive is the value itself. Unlike rice that can be dried, corn that can sit in storage, or seafood that can be frozen immediately after harvest, crawfish enter the market in an extremely fragile state. They must stay alive. From the moment they are pulled from the water, the clock begins ticking. Under Louisiana's hot and humid conditions, every sack of crawfish must be transported back to shore, weighed, sold, washed, cooled, and moved into cold storage as quickly as possible. If the process slows down, the crawfish may die before reaching buyers. And once they die, their value drops rapidly. The meat becomes softer, the flavor deteriorates, commercial quality declines, and a shipment that once promised profit can suddenly become a financial risk. That is why the crawfish industry operates through a highly specialized cold chain system, one designed not only to preserve food, but to preserve life itself. Trucks, ice, cooling facilities, ice-making machines, delivery schedules, and processing speed all become survival tools for the product. A single company may purchase tens of thousands of pounds of crawfish every day, but larger scale also means greater risk. In 2024 alone, Louisiana produced more than 128 million pounds of farm-raised crawfish for the market. At that scale, a delayed truck, a refrigeration failure, an unexpected heat wave, or even a slow sales day can cause thousands of pounds of live crawfish to lose their value before they ever reach consumers. Not every crawfish is large enough, attractive enough, or healthy enough to be sold whole for traditional crawfish boils. But that does not mean they lose their value. Smaller crawfish, or those outside the premium category, are sent to processing plants, where they are transformed from short-lived live animals into food products that can travel farther, last longer, and remain available year-round. At the factory, crawfish are washed once again to remove any remaining mud and debris before entering the steaming or boiling stage. Within minutes, their dark shells turn bright red. But the most valuable part of a crawfish is actually very small, the tail meat. To produce just 1 pound of packaged crawfish tail meat, workers must peel countless crawfish by hand, repeating the same motion thousands of times each day. The extracted meat is then cleaned, packaged, vacuum-sealed, and stored under refrigeration. Thanks to this processing stage, crawfish are no longer limited to seasonal meals in Louisiana. They can travel across the country, appearing in restaurants, supermarkets, industrial kitchens, étouffées, boudin, soups, sauces, and countless Cajun dishes throughout the United States. So what makes this million-dollar dish so special that Americans, especially people in Louisiana, are so obsessed with it? First, crawfish is defined by the way it is eaten. A typical crawfish boil begins with steam rising from a pot infused with bold Cajun spices, where sweet corn, soft potatoes, smoky sausage, and bright red crawfish all come together in a rich, irresistible aroma. When the entire batch is poured out onto the table, the red shells, golden corn, spicy fragrance, and rising heat instantly transform the meal into something unique, intimate, lively, and full of energy. The flavor of crawfish is just as distinctive. The tail meat is sweet, tender, and slightly infused with the boiling broth. It carries the lightness of shrimp and a subtle richness reminiscent of lobster, yet it has its own identity shaped by Cajun seasoning, spicy, savory, and deeply layered. Each time you peel the shell, pull out the tail, dip it into sauce, and take a bite, it becomes an addictive rhythm of eating. But what truly makes crawfish a cultural symbol of Louisiana is not only its taste, it is the atmosphere it creates. Crawfish boils are moments when family, friends, and neighbors gather around the same table. People peel, eat, talk, and share a spread of vibrant food together. In Cajun culture, it represents the flavor of festivals, weekend gatherings, music, laughter, and Southern hospitality. From crawfish boils to étouffées, boudin, and Cajun sauces, crawfish has become part of Louisiana's culinary memory, a small crustacean carrying the taste, rhythm, and pride of an entire region. Behind the vibrant red crawfish boils, steaming pots of Cajun seasoning, and the lively atmosphere of communal feasts lies an industry far more fragile than it appears. Crawfish can generate hundreds of millions of dollars for Louisiana, but maintaining that value requires farmers, traders, and processing plants to constantly manage multiple risks at once. This is not an industry where harvest ends and stability begins. Crawfish are live products. They depend on on-time trucking, reliable cold storage, ice, refrigeration systems, workers for sorting, transporters, peelers, and a market fast enough to absorb peak season supply. If even one link slows down, the entire value chain can collapse. A broken-down truck on the road is not just a transportation issue. It can cause dozens of sacks of crawfish to weaken under the heat, turning a single buying day into a major financial loss. This pressure also extends to labor. During peak season, work does not follow a standard 8-hour rhythm. Instead, it follows the cycles of water, temperature, trap yields, and market demand. Workers may begin before sunrise and continue for long hours in hot, humid conditions. The 2024 season served as a clear reminder of this fragility. After droughts, extreme heat, saltwater intrusion, and a severe cold snap, the LSU Ag Center estimated that Louisiana's crawfish industry could suffer nearly $140 million in losses. As supply tightened, crawfish prices in some areas rose to around $10 to $12 per pound, compared to $3 to $5 per pound the previous year. These figures show that risk in the crawfish industry is not theoretical. It can appear quickly. From dry, cracked fields, overloaded cold storage facilities, to rapidly shifting market prices. But the greatest risk remains the weather, because crawfish depend almost entirely on shallow water, mud, temperature, and environmental stability. A single extreme weather event, from prolonged droughts that dry out fields to unexpected cold spells that slow growth, can severely disrupt an entire season. On the dinner table, crawfish may represent joy, warmth, and celebration. But within the supply chain, they are a constant gamble with time, cost, and nature itself. From a mud-dwelling crustacean, crawfish has evolved into a major food industry in Louisiana. It generates additional income for farmers, sustains jobs, and supports restaurants, festivals, and an entire supply chain behind it. But the story of crawfish also reveals a more complex truth. No species is purely an asset or a disaster. Everything depends on where it appears, how humans manage it, and the boundaries we are disciplined enough not to cross. For most of human history, growing rice meant manual labor, unpredictable weather, and high risk. But as the 20th century began, everything changed at a pace that was hard to imagine. Rice transplanters replaced dozens of hands in the fields. Combined harvesters shortened harvest seasons from days to just hours. Nitrogen fertilizers accelerated plant growth and made yields more uniform. Pesticides allowed farmers to control pests across vast areas with a single spray. Rice cultivation entered an era of standardization and scale. In the short term, the system functioned almost perfectly. Output surged, and harvests became more stable. Yet that very efficiency concealed silent fractures. Repeated pesticide use pushed pests to evolve resistance faster. Excess fertilizers washed into rivers and lakes, triggering eutrophication and polluting water sources. Soils gradually lost beneficial microorganisms and became increasingly dependent on chemical inputs. Slowly, a paradox emerged. Production increased, but profits declined. The costs of fertilizers and pesticides kept rising, while the land responded less and less to the very chemicals that once drove its productivity. And as these limits grew impossible to ignore, a question surfaced. Is there any path forward other than pouring ever more chemicals into rice fields? The answer did not come from high-tech laboratories, but from agricultural history itself. In the early 2000s, groups of scientists in China, Japan, and Southeast Asia began to re-examine farming systems that had long been neglected. Among them, the rice duck system emerged as a particularly striking case. Rather than dismissing it as outdated folk practice, researchers brought this model into controlled experiments and measured its effects with concrete data. The results surprised many. Rice fields integrated with ducks recorded a 50–70% reduction in pesticide use, along with clear declines in herbicides and chemical fertilizers. Some studies even showed yield increases ranging from 7% to more than 15%, especially in fields suffering from soil degradation. In China, provinces such as Zhejiang, Fujian, and Guangdong saw farmers gradually reintroduce ducks into their rice paddies. At first, these were only small, exploratory trials. But as the results repeated themselves across multiple growing seasons, the model quickly scaled up, from a handful of plots to entire farming regions. So why ducks, and not some other animal? In the rice duck system, ducks are not auxiliary livestock kept outside the production process. They are an integral part of cultivation, true ecological engineers. Few animals are as naturally suited to rice paddies as ducks. They thrive in shallow water, move constantly yet lightly, and when introduced at the right stage, they cause almost no damage to the rice plants themselves. Instead of feeding on rice, ducks focus on exactly what farmers want to remove. They consume harmful insects such as brown plant hoppers and stem borers, along with various aquatic organisms that compete with rice for nutrients. At the same time, ducks pick at young weeds, disrupting their life cycle before they have a chance to establish and spread. The most significant impact, however, comes from movements that seem almost ordinary. As ducks walk through the fields, they stir the water in the top layer of soil. This agitation breaks up anaerobic conditions, increases oxygen exchange, improves soil structure, and reduces methane emissions, one of the most potent greenhouse gases in agriculture. Rather than trying to eliminate each problem with chemicals, the rice duck system allows biology to regulate itself. It is this reversal in logic that creates a fundamental difference and explains why the rice duck model is both praised as a sustainable solution and questioned within the framework of modern, chemical-dependent agriculture. When ducks are released into rice paddies, the farmer's biggest concern emerges immediately: yield. No matter how balanced an ecosystem may be, it becomes meaningless if productivity declines. For many, introducing animals into actively cultivated rice fields sounds like an unacceptable risk. Yet reality moves in the opposite direction. When managed correctly, ducks do not damage the rice. They are typically released about 2 to 3 weeks after transplanting, when the rice plants have become strong enough. Rather than feeding on the crop itself, the ducks largely ignore the rice and focus on insects, aquatic organisms, and young weeds. As pest pressure decreases and soil structure improves, rice plants experience less stress. Their roots develop more steadily, nutrient uptake becomes more efficient, and growth grows increasingly uniform over time. At the same time, the paddy begins to change in visible ways. Beneficial insects return. Frogs, small fish, and dragonflies reappear. The water becomes clearer with less algae. The rice field no longer operates like a chemical-dependent production factory, but gradually returns to the state of a living ecosystem. And once that ecosystem is restored, yield no longer has to be sustained by increasing chemical inputs. It begins to emerge from the stability of the system itself. The benefits of the rice duck system do not end at the edge of the paddy. As the season progresses, the ducks grow alongside the rice, drawing on a natural food supply of insects and aquatic organisms. As a result, they develop robustly without the heavy reliance on industrial feed or antibiotics common in intensive livestock systems. By the end of the growing season, the ducks are no longer merely ecological tools, but economic products. Farmers can sell duck meat or eggs, creating a direct source of income in addition to rice. For many smallholder households, this added revenue is enough to offset production costs, and in some cases, generate profit even when rice prices fluctuate. At the same time, the value of the rice itself changes. In many regions, rice produced under the rice duck system is marketed as ecological or low-chemical rice, often commanding prices 10 to 30% higher than conventional rice. Consumers are increasingly willing to pay a premium for products associated with environmental protection and human health. More importantly, this model helps farmers escape complete dependence on a single crop. Instead of placing all their risk on one rice harvest, they gain multiple, parallel income streams. In an agricultural landscape growing ever more unstable, that very diversity becomes the factor that allows farmers to remain resilient. If the rice duck model in China carries the character of a grassroots revival driven by farmers' practice, then in Japan it was taken one step further: standardization. Beginning in the 1980s, Takao Furuno developed the Igamo method, transforming a traditional biological system into a tightly controlled farming process. The most distinctive feature of Igamo lies in its management discipline. Ducklings are released into the paddies at precisely calculated densities, at exactly the moment when rice plants are strong enough, and are removed before the rice enters the flowering stage. There is no room for randomness. Every step is designed to minimize risk to yields. As a result, Igamo rice fields require virtually no pesticides or synthetic fertilizers, yet yields remain comparable, often more stable, than those of conventional chemical-based farming. More importantly, Igamo rice has been strongly embraced by the Japanese market, typically selling at a premium of 20 to 30%, thanks to its reputation for quality and environmental responsibility. Compared with the rice duck model in China, Igamo makes one point clear: biological farming does not rely on nature alone. It also demands discipline and scientific design. It is precisely this combination that has allowed an ancient method to survive and thrive within one of the world's most demanding agricultural systems. Despite its promise, the rice duck system is not a miracle solution that can be applied everywhere. In reality, it is a system that demands strict discipline and precise management. If ducks are released at the wrong time, when rice plants are still too young, an entire field can be trampled within hours. If they are removed too late, the ducks may damage the rice panicles during the most sensitive stage of the growing season. Ducks also bring their own set of risks. They must be protected from predators such as foxes, snakes, and birds of prey. This requires fencing, human supervision, or additional protective measures, investments that not every farming household is willing or able to make. Water management presents another challenge. Unstable water levels can reduce the ecological effectiveness of the system, or even cause it to backfire. More importantly, the economic performance of the rice duck model depends heavily on market conditions. Not everywhere are consumers willing to pay a premium for ecological rice or low-chemical products. Without suitable market access, the economic advantages of the system diminish significantly. For these reasons, rice duck farming is not a comprehensive replacement for industrial agriculture. Rather, it is an option that must be carefully evaluated, one that works best when matched with local conditions, management skills, and access to supportive markets. As the rice duck system began to show clear results, some farmers raised a follow-up question. If ducks can help rebuild the surface layer of the rice paddy ecosystem, then what is happening beneath the water? And could that ecological layer be used more effectively? From that question, the rice-fish-duck system emerged. Fish were introduced into rice paddies to take on roles that neither chemicals nor ducks could fully address, controlling larvae, plankton, and excess organic matter in the water layer. In this system, each component operates in a different layer. Fish live and feed below the water's surface, consuming mosquito larvae, insect eggs, and organic debris. Ducks operate at the surface, controlling pests and weeds while stirring the water. Rice occupies the growth layer above, benefiting from the activity of both. The three layers do not compete, they complement one another. Compared with traditional rice-fish farming, the addition of ducks makes the system more closed and self-regulating. Fish handle what happens below the water, ducks manage what occurs at the surface, and rice becomes the central recipient of nutrients. As a result, the need for fertilizers and pesticides continues to decline, while the ecosystem remains more stable across multiple seasons. In parts of China, Vietnam, and Bangladesh, this model has proven especially effective under prolonged flooding conditions. When rice faces risks from floods, fish and ducks can still thrive, acting as an economic safety net for farmers. Instead of relying on a single product, they harvest rice, fish, and ducks from the same field. However, this system also demands a higher level of management. Fish density, the timing of duck release, and water level control must all be carefully calculated. Not every location is suitable. But in places where conditions align, the rice-fish-duck model demonstrates an important principle. When ecosystems are properly designed, agriculture does not have to choose between productivity and sustainability.